Quantum Chromodynamics. Quantum chromodynamics is the branch of physics that describes the fundamental interactions between the smallest particles known as quarks and gluons, which are the building blocks of protons, neutrons, and other particles in the nucleus of an atom. In simple terms, quantum chromodynamics helps us understand the strong force, one of the four fundamental forces of nature, and how it holds together the particles that make up matter. To start with, it's important to know that all matter in the universe is made up of atoms. Atoms consist of a nucleus, which contains protons and neutrons, and electrons that orbit around this nucleus. However, if we zoom in on the protons and neutrons themselves, we find they are not the smallest building blocks. Protons and neutrons are made of even smaller particles called quarks. Quarks are held together by another particle called a gluon. Now, the main goal of quantum chromodynamics is to explain how quarks and gluons interact. The term chromodynamics comes from the word chroma, which means color. However, this color in quantum chromodynamics does not refer to the colors we see with our eyes. Instead, it refers to a property of quarks similar to electric charge in electromagnetism. Quarks come in three colors: red, green, and blue. Gluons are responsible for exchanging these colors between quarks, effectively holding them together. The idea is that, just as positive and negative electric charges attract in electromagnetism, the different color charges in quarks attract each other in quantum chromodynamics. Quarks cannot exist in isolation, they are always found together in groups. The most common groups of quarks are pairs of three quarks, which make up protons and neutrons, and pairs of a quark and an antiquark, which make up particles called mesons. Quantum chromodynamics explains why quarks are confined within these groups and why we can never see them on their own. The force that holds quarks together, mediated by gluons, becomes stronger the farther apart the quarks get. This is the opposite of how forces like gravity or electromagnetism work, where the force gets weaker with distance. Because of this property, quarks are permanently bound together, a phenomenon called confinement. The force between quarks and gluons, known as the strong force, is the most powerful of all the fundamental forces. It's much stronger than gravity, electromagnetism, or the weak force, which is responsible for radioactive decay. In fact, the strong force is what binds protons and neutrons together in the nucleus of an atom, despite the fact that protons all have a positive charge and would naturally repel each other. Without the strong force described by quantum chromodynamics, atoms, and therefore all matter, would not be able to exist. The strong force operates at extremely short distances, typically less than the size of an atomic nucleus. The gluons, which carry this force between quarks, are themselves affected by the force. This is different from other force-carrying particles like photons in electromagnetism, which do not interact with each other. In quantum chromodynamics, the gluons can emit and absorb other gluons, which makes the behavior of quarks and gluons very complex and dynamic. One of the key principles in quantum chromodynamics is called asymptotic freedom. This means that at very short distances, or at very high energies, the strong force becomes weaker. Quarks and gluons behave almost like free particles when they are very close to each other. This principle was discovered in the early 1970s and led to a greater understanding of how particles behave at extremely high temperatures and energies, like those found in the early universe right after the Big Bang. On the other hand, at lower energies or longer distances, the strong force becomes incredibly strong, leading to the confinement of quarks inside protons, neutrons, and other particles. This means that no matter how much energy we put into separating quarks, we can never observe them alone. Instead, when enough energy is added, new quark-antiquark pairs are created, and we end up with more particles, not isolated quarks. Quantum chromodynamics is also closely related to the study of particle collisions, such as those that take place in particle accelerators like the Large Hadron Collider. When particles are smashed together at high speeds, the energy involved can briefly overcome the confinement of quarks, allowing scientists to study the properties of the strong force and the behavior of quarks and gluons. These high-energy collisions help physicists explore the inner workings of protons and neutrons, and test the predictions made by quantum chromodynamics. One of the challenges of quantum chromodynamics is that the equations describing the interactions between quarks and gluons are incredibly complicated. Because gluons interact with each other as well as with quarks, the calculations involved in predicting the behavior of these particles are much more difficult than those in simpler theories like electromagnetism. However, advanced techniques such as lattice quantum chromodynamics, which involves using powerful computers to simulate the behavior of quarks and gluons on a grid or lattice, have helped physicists make progress in understanding the strong force. Quantum chromodynamics also has implications beyond the physics of everyday matter. It plays a crucial role in the study of the early universe, where temperatures and energies were so high that quarks and gluons were not confined inside protons and neutrons. Instead, they existed in a state known as quark-gluon plasma, where they could move freely. This state of matter is believed to have existed for only a tiny fraction of a second after the Big Bang, but by recreating conditions similar to those in the early universe using particle accelerators, scientists hope to learn more about how the universe evolved and how matter as we know it came into existence. In conclusion, quantum chromodynamics is a fundamental theory in physics that explains the behavior of quarks and gluons, the particles that make up protons, neutrons, and other matter. It describes the strong force which holds these particles together and is responsible for the stability of atomic nuclei. Although the theory is complex, it has been essential for our understanding of the universe at both the smallest and largest scales, from the behavior of individual particles to the evolution of the cosmos.